Hello, Algebra 2 students. This is a lecture on using recursive rules with sequences. This is going to be a different unit than the rest of Chapter 12 because the way that we're defining our sequences has completely changed in Section 12.5. I'm going to go into more details on that here in a second, but first let's talk about some terms. Explicit rule. I haven't used this term yet, but what we are doing if we are defining something explicitly, or if I give you an explicit rule, is I am defining a sub n as a function of the term's position n. So let's think of an example to help us to illustrate what this would look like. In section 12.3, we talked about geometric sequences, and a geometric sequence that I could potentially give you would be a sub n is equal to a sub 1. This is the formula for them, right? A sub 1 times r to the n minus 1, or actually filling in the numbers, a sub n is equal to, let's just say 3 times 2 to the n minus 1. So if I wanted to know the fifth term, I would just take 5 and I would plug it in for n here, and that would tell me the fifth term. If I wanted to know the 10th term, I would take the number 10 and plug it in for n, and it would tell me what I would get out would be the 10th term. Everything from 12.1 to 12.4, 12.1 through 12.4 has been explicit rules. I want to know the 10th term, I plug in 10. I want to know the fifth term, I plug in 5 into the rule. However, in section 12.5, we're going to shift gears a little bit, and we're going to start defining things recursively, or using a recursive rule. With recursive rules, I'm going to define the beginning term, or sometimes terms, and then I'm going to say, hey, the nth term is very similar to the term that came before it, and then it will say how it's different than the term that came before it. That's it. So this is going to be a little bit more challenging. If you wanted to know, let's say here, if we wanted to know the fifth term, I might say, well, it's 4 more than the fourth term. And then you're like, I don't know the fourth term. The fourth term is 4 more than the third term. And the third term is 4 more than the second term. And you have to work your way all the way back to the first term, which will be defined at the beginning. So I'm not giving you the ability to just be like, I want to know the 10th term, plug in 10. If you wanted to know the 10th term, you would have to literally find out the 9th term, then the 8th term, then the 7th term, then the 6th term, then the 5th term, and you would work your way all the way up because you don't know the 10th term. You only know how it relates to the one that came before it. We want to easily be able to denote or write the previous term. So instead of saying, hey, 4 more than the previous term, right, than the previous term, what we're going to say is 4 more than a sub n minus 1. 4 more than the term that came before it, a sub n minus 1. So anytime you see a sub n minus 1, that means the one that came before it. What do you think a sub n minus 2 means? That means the 2 terms that came before it. Let's look at an example here. Write the first 6 terms of the recursive sequence. So in this problem, I'm going to say, the 0th term is 1, a sub 0 is 1. I want to know a sub 1 next. I already know the a sub 0th term. The next term would be a sub 1. I need to know what a sub 1 is. So what we did was we plugged 1 in here, and then we would also have to plug 1 in there. Well, a sub 1 is equal to a sub 1 minus 1 would be a sub 0, yes? And then plus 4. What is a sub 0? Well, that was just defined right here as 1. 1 plus 4 is 5. So the first term is 5. Well, what about a sub 2? Right, we have to find the first 6 terms. A sub 2, if I plug 2 in as the thing that I want to know about, right, then I would also plug 2 in there, because I'm plugging 2 in for n. A sub 2 minus 1, well, 2 minus 1 would be a sub 1 plus 4. Well, what is a sub 1? I already found out what a sub 1 is. It's 5. 5 plus 4 is 9. So my pattern, a sub 0 is 1, a sub 1 is 5, a sub 2 is 9. You could probably look at this and pick out what a sub 3 is, but let's go through the steps. If we want to know what a sub 3 is, we'd plug 3 in for that n and 3 in for that n. A sub 3 is, well, 3 minus 1 is a sub 2, right? We know what 3 minus 1 is. It's a sub 2. A sub 2 plus 4. What is a sub 2? A sub 2, we already found out a sub 2 is 9. 9 plus 4 would be 13. Right? We could use this pattern forever, and we could keep doing this. But if I wanted to know a sub 50, that becomes pretty tricky, because a sub 50 is a sub 49 plus 4. Well, what's a sub 49? I don't know. I have to build my way all the way up to a sub 49. So that is why recursive rules are different. You're always defining the term as how it relates to the previous term. And remember, the previous term, we use this notation to represent the previous term. And we saw why it works that way, because we took 1 away from this number every time. So it's 1 less. A sub 2 is equal to a sub 1 plus 4. A sub 3 is equal to a sub 2 plus 4. Let's move on to the next one. Write the first 6 terms of this sequence. In this problem, I'm starting out with a sub 1. It doesn't really matter which one you start out with. A sub 1 is 1. The next thing that I would want to know is a sub 2. A sub 2, so I'm plugging 2 in for that n, and I would also have to plug in 2 for that n. It would be 3 times a sub 1. Well, a sub 1, we already found out is 1, so it's just 3. 3 times 1 is 3. Moving on, the next term I would want to know is a sub 3, so I'm plugging a 3 in for that n and a 3 in for that n. 3 minus 1 is 2, so it ends up being 3 times a sub 2. A sub 2 we found out was 3. 3 times 3 is 9. And hopefully you guys would be able to follow this forever if I gave you some really trivial task and I said, hey, produce the first 100 numbers, right? Hopefully you'd be able to do that, because it's not really that tricky, but I really want you to be understanding the notation and how this is going to work. A sub 4 is, if I plug in 4 there, I would also have to plug in 4 for that n, and 4 minus 1, a sub 4 minus 1 is actually a sub 3, so 3 times a sub 3. A 3 we already know is 9, 3 times 9 is 27. We could keep doing this if we needed to. Hopefully you feel like you understand that pattern. So one question that I think would be a really appropriate question for you to be asking is, this seems like way more work than explicit rules. And we could write this exact same rule right here, 1, 5, 9, 13. We could write that explicitly from 12.2 or recursively. And we could write this rule right here, explicitly or recursively. So this rule, defining the first term, and then this part of the rule is the exact same sequence if we used the stuff from 12.3. A1 is 3 in the R value. What you're multiplying by is 3. So it's the exact same sequence as a sub n is equal to A1 R to the n minus 1. A1 was 1, and R is 3. Okay, this is this exact same rule. This is defining it recursively, and this one down here is defining it explicitly. So why do we need both? And I have 2 answers for you for that question. One is, it's really easy to write the rule recursively. This part, if I gave you the rule and asked you to write the rule, and I'm going to do that, is really easy to do recursively. And the second part is, this actually allows us to write rules of sequences that would be really hard, if not impossible, to write explicitly. And the most famous sequence of all sequences, and most of you guys have heard of this, I know I've kind of alluded to this earlier, is the Fibonacci sequence. And if you are unfamiliar with the Fibonacci sequence, I highly suggest you watch the video I have posted on Schoology. That it's not me, it's a TED Talk, but the mathematician does a great job of pointing out tons of different applications for the Fibonacci sequence in nature, like with rose petals and pineapples and tons of different other things. There's applications in the stock market and in like the human body. There's tons of different applications that relate to the Fibonacci sequence. And the Fibonacci sequence is actually a recursive rule, not an explicit rule. It would be very difficult, if not impossible, to write explicitly, but recursively we can do a really good job of it. So that's my answer for you for why we have to have an explicit way and a recursive way to write these rules. Before we go into the Fibonacci sequence and some things like that, some of the examples are going to be a little bit more complicated, like this one here. So a sub 0 is my first term that's defined, and then here is the rule part of it. So a sub 0 is 64. The next term I would want to know would be a sub 1, so I plugged 1 in everywhere where there's an n. So a sub 1 would be 0.5 times a sub, if I'm plugging in a 1 there, that would be 0, plus 2, if I plug in a 1 there and there, I'm also plugging in a 1 there, of course. So it would be 0.5 times 64, because a sub 0 we know is 64, plus 2. So 32 plus 2 would be 34. And then I could do this again with the next term. A sub 2 is 0.5. I'm plugging 2 in there, there, and there. That's a full size one. These ones are in like the subscript. 0.5 times a sub 1 plus 2 times 2. 0.5 times a sub 1. I know a sub 1 is 34, so 0.5 times 34 would be 17, plus 4 would be 21. And hopefully you guys would feel confident continuing to write this rule. A sub 3 is 0.5. I'm plugging 3 there, there, and there now. 0.5 times a sub 2 plus 2 times 3. Well, a sub 2 is 21. Half of 21 would be 10.5, and 10.5 plus 6 would be 16.5. And we can continue to do this if we needed to up to the sixth term. So one of the benefits of recursive rules that I talked about is it's really easy to write the rule for them. If it's an arithmetic, there's going to be 3 different varieties of this that I'm going to quiz you on. I'll start with that. It's going to be either arithmetic, and this is the way to write that. It could be geometric, and this is the way to write that. Or it could be neither. In all of the types that are neither, I'm going to kind of guide you through how I want you to think about that coming up. But first, let's start with the arithmetic and geometric parts. And then big star here, reminder, you must define first term, or you will be half wrong if you don't define the first term. You will never be able to produce the sequence if you don't have the first term. It's built upon that. So make sure you do include the first term. All right, let's take a look at an example here. So write a rule for the following sequence. Hopefully you look at this right away and you're like, boom, arithmetic. Okay, I can tell that it's arithmetic because we are adding a constant between consecutive terms. Add 10, add 10, add 10. It's arithmetic. The rule for this is going to be a sub n is equal to a sub n minus 1 plus 10, because that's the common difference, d. And then we also just need to write the first term. A sub 1 is 3. This is all you need to write a rule for a recursive sequence. I think you can see why that's really simple, right? That's one of the benefits of recursive rules. This one here, we're going to notice very quickly that it's not arithmetic because we are not adding a constant between consecutive terms. This one's plus 150, plus 60, plus 24. It's not common. However, there is a common ratio. If you divide a term by its previous term, 250 divided by 100, 100 divided by 40, 40 divided by 16, you're going to get 5 halves or 2.5. So our value is 2.5. We can define the first term, and that's 16. And then a sub n is equal to 2.5 times a sub n minus 1, and that's it. Here would be some easy ones for you to try, pause it, see how you do. I'm going to quickly write them. So pause it here, try them. This one would be a sub 1 is equal to 11, and a sub n is equal to a sub n minus 1 plus 11. And then this one would be a sub 1 is equal to 324. And a sub n looks like we're dividing by 3, which is the same as multiplying by a third. So the r value is 1/3 a sub n minus 1. So what about if our example is not arithmetic or geometric? You look at the pattern and you're like, we're not adding a constant, we're also not multiplying by a constant. Then that's going to shift you into this different variety. And this first example here is actually the Fibonacci sequence that I talked about earlier. And it's a very unique pattern. And what it is, I'll give you a second to think about it here. The third term is the sum of the previous two terms, 1 and 1. The fourth term is the sum of the previous two terms, 1 and 2. And that's going to continue on forever. So 8 is the sum of 3 and 5. Hopefully that could mean that you guys would be able to write the next term. The next term in the Fibonacci sequence would, of course, be 13, because 13 is 5 plus 8. Just add the next two numbers, and it would produce the following one. Like I said, I highly recommend you watch the video on Schoology. I think it's very entertaining, and it gives you a good foundation for what the Fibonacci sequence is. But here is the Fibonacci sequence. Now, how do we write the rule for the Fibonacci sequence? When I gave you guys the definition for a recursive rule, I said define the beginning term or terms. If it is not arithmetic and not geometric, you are going to define the first two terms, because that's what you're essentially recalling, right? You want to be able to say the third term is the previous term and two previous terms. So what you're going to do is you would say a sub 1 is 1. A sub 2 also happens to be 1 in this example, right? The first term is 1 and the second term is 1. And then the third term is the sum of the previous one and two previous. The fourth term is the previous one and two previous. That's true for every situation. A term is the sum of the one that came before it and the one that came before that. And so using the notation, okay, what notation do we have for the previous term, right? A sub n minus 1. And what notation do we have, kind of, maybe you have to infer it a little bit. What notation do we have for two previous? That would be a sub n minus 2. This is how you write the Fibonacci sequence. And we should be able to just verify, you should be able to take this sequence and produce this rule. We know the first term, we know the second term. The next thing that we'd want to know would be the third term. A sub 3 is equal to a sub 2 plus a sub 1. That's exactly what the Fibonacci sequence is, right? The third term is the second term in the first. The fourth term is the third term in the second, and so on and so forth. So all of the ones that are not arithmetic and not geometric are going to have the same pattern, very Fibonacci-like. Okay, let's start with this one. Well, I know right away that it's not arithmetic because we're not adding the same thing. I know right away that it's not geometric because we're not multiplying by the same thing. So then it goes to this separate category, and all of the separate categories, you can just start by defining the first term and defining the second term. Now, how do these two numbers make the third term? And does that pattern hold? Okay, how would 2 and 2 make 4? How would 2 and 4 make 8? How would 4 and 8 make 32? Hopefully you're seeing this pattern relatively quickly. It's always going to be really similar, right? So what we want to say in this problem, hopefully you're picking up on the pattern, is the third term is the one that came before it, and 2 that came before it multiplied. 1 and 2 times each other make 2. 2 and 2 times each other make 4. 2 and 4 times each other make 8. So what you want to say is a sub n is the term that came before it times the term that came before it, a sub n minus 2. And that would be how we would write the rule for this particular non-arithmetic or geometric recursive sequence. Please let me know if you guys have any questions, and hopefully recursive rules makes a little bit of sense. Thanks, guys.